Welcome to the second lecture. Give me a second here to get set up. And we are on Lewis structures. 1.3 is where we'll start. .3 is Lewis structures. We call these also electron dot representations. Let me give you a few rules. Sometimes from time to time I'll give you a list of rules and then we'll do problems. And so the list of rules is meant to be a guideline, not something to memorize. We want to draw only valence electrons as opposed to core electrons. We're not going to draw all the electrons, only the valence electrons, because that's what we're concerned with. Maximum of 2 electrons for hydrogen. 3, max 8 electrons for second row. That's what we'll be dealing with. Let's look at some examples of Lewis structures with single bonds only. We'll start with that. And so here's sort of some rules, and then here's some steps. Number 1, you want to arrange the atoms. So you'll be given a formula. You want to arrange the atoms. I'm going to count valence electrons, arrange the electrons, and I'm going to call it count formal charge, just to give us a way to remember this. Okay, arrange count. Okay, we'll talk about formal charge when we get there. We can also use the term assign, but we're going to arrange, we're going to count, we're going to arrange, and we're going to count. Okay, and so let's look at some examples of this. Start with a pretty simple one. It's a lot like a molecule you've seen before. You've seen HCl, I'm sure. So let's look at HF. I give you HF, that's a formula. And you need to draw the Lewis structure. So the first thing we do is arrange the atoms. It's pretty simple in this case. We have 2 atoms. There's no other way to arrange them. That's step 1. Here I'm doing the steps that we just talked about. So I'm going to arrange. I'm going to count the number of valence electrons. How many is it? Hydrogen, it's 1. Okay, it's the column that it's in. It's the group number. Okay, so hydrogen is 1. Fluorine is 17 or 7. It's not 17 electrons. It's 7 electrons. So that's 1 plus 7 is 8. You got 1 from the H, 7 from the fluorine. So now we need to arrange the electrons around our H and our F. Hydrogen can only have, it has 1 electron. It brings 1 electron into the molecule. Fluorine brings 7. 1, 2, 3, 4, 5, 6, 7. Okay. Again, as you work on these, you'll start skipping steps, but we can imagine we're gonna show electron moving a lot later in the course. We can imagine these electrons kind of reaching out and forming a 2-electron bond. Okay, again, there's energetic stability for them to come together. Even though there's repulsion initially between electrons because they're both negative, there's value added. There's energetic value added. When they come together, they form a bond. Okay, we'll talk about bonding later and the energetics of that. But we form a bond, and we're going to draw this now as HF What are they doing? They're both sharing one electron. Fluorine has 3 pairs that are not being shared. This will become important later. And now they've both achieved filled shells. Fluorine is it's 2. That's a stray mark. The fluorine is the level 2 is filled with 8. The hydrogen, the level 1, is filled with 2. Okay, this is so important that you spend the time understanding these concepts. And we draw this like this now. We use a line to indicate a bond. And we draw the pairs. Okay, so we need to draw all the electron pairs. You've got to show the lone pairs on your Lewis structures. So we arrange the atoms, we counted electrons, we arrange the electrons, and now we count formal charge. And we'll go into that when we have negative and positive charges. Okay, well, you can practice this. It's a good way to go back and convince yourself that the formal charge is 0. Okay, we'll get to formal charge with negative and positive, but we're always calculating formal charge. Okay. All right, so let's do another one. Give you CH4. So now we've got some more atoms. Okay. But I've given you a big hint. Hydrogen can only have one bond. So you're not going to line up your hydrogens as if they're going to bond to one another. Okay. And we know that carbon's valence number is 4. So we're going to arrange these atoms in the only way possible, basically, telling you those rules. Why can hydrogen only form one bond? Because its shell only has one orbital. It cannot contain any more electrons. So we arrange the atoms. We're going to count the valence electrons. How many? It's 8. Where did we get that number? We have 1 from each hydrogen times 4 of those. That's 4. Plus, we have 4 from carbon. So that's 8. Step 3, we're going to arrange the electrons. We're going to assign the electrons to each of the atoms. Hydrogens each have 1. Kind of arrange them like this. How many is carbon bringing into the table, or into the equation, so to speak? 4. Okay. This carbon, the way I've drawn it, is not representative of its actual configuration. Okay, we'll get to that later. But these electrons are going to share. An arrow with a fishhook indicates the movement of 1 electron. Okay. So we can draw that now as this. There are no lone pairs in this case, so that is your Lewis structure. That is 100% credit on an exam question. Formal charge, again, just to introduce you to the term, is 0. Okay, we're going to go through how to calculate that with pluses and minuses. Let's do a couple more examples. More sophisticated atoms. I'll give a couple more, and then I'll give you some kind of take-homes. CH3Cl we could start with that, CH3. We know that hydrogen can only form 1 bond. Chlorine, again, I'm going to tell you that fluorine, chlorine, bromine, iodine, generally speaking, form 1 bond. So they're going to look like a hydrogen in that sense. They're going to have lone pairs. Okay. Step 2, valence electrons. How many is it? It's 3 times 1 for each hydrogen. It's 4 for a carbon. How many for chlorine? Now, it's not total electrons. It's the group number. It's the column number, and that's 7. Got 7 from the chlorine. What does that come out to? 14. 14 is our total number. So now we have to distribute these electrons. And if we've already kind of drawn our frame, we can skip the step of redrawing the atoms. Again, I'm not going to make you go through this whole process. There's 4 for carbon, 3 for hydrogen. That's only 7. So we have 7 more that we have to account for. There's 6, 7. You see, and again, if you want to skip the arrows, you can start to draw lines. Connect the dots. Please redraw it for me very clearly. Got to include lone pairs. You must include that for a proper Lewis structure, but that is the correct answer. Okay, so we arranged the atoms, we counted electrons, we arranged the electrons again, and then we counted formal charge. Again, it's 0. I'm just going to keep mentioning that. So let me do one with a formal charge, and then I'm going to give you some take-home assignments. Take-home meaning we can do them in class. You should work these on your own. I'm going to give you CH3 and tell you this has a minus charge. So the way this works is molecules have real charge. Okay? They have real charge, and we use a term called formal charge. And formal charge means we want to assign an atom to have a charge. Okay? And so we have to account for the charge. A charge of -1 means there's an extra electron that we have to account. So let's go ahead and arrange our atoms, step 1. It's the only way they can be arranged. We're not going to do a lot of Lewis structures with metals like sodium. You should always assume sodium is sodium plus, lithium plus. Those in the first column, they're going to be sodium plus, lithium plus, potassium plus, calcium 2 plus, magnesium 2 plus, etc. And you'll see those when we get there, okay? But let's calculate, or I'm sorry, let's calculate the number of valence electrons here. We have 3 from the hydrogens, we've got 4 from the carbon, and we've got an extra 1 electron. That's the charge. A negative charge adds an electron. People get this backwards sometimes. They say negative, they take 1 away. You're not taking an electron away, you're adding an electron. So that gives us a total of 8. 8 is our valence number. So step 3 now is that we want to arrange these electrons. We arrange the atoms, we count the electrons. We're going to arrange electrons. And now arrange them just like you would any other carbon atom, right? A hydrogen, that extra electron cannot go on the hydrogen because it's going to form bonds, right? We got 1 extra electron, and we wonder where that's going to go. Well, it has to go on the carbon. It's not just floating around in space. It's got to be on an atom. So now that we've added an electron to carbon, and we'll talk about how we calculate this number, there is a formal charge on carbon. So there's a charge on the molecule. The formal charge, meaning the assigned charge, goes on carbon. And so you would draw it like this. Would be the best way to draw this. And you put a little negative right next to the atom, not over here like that. Okay, and not with brackets like that. I've just used the brackets to indicate that the molecule itself has a charge. Formal charge goes on an atom. Okay, and it can never go on hydrogen, basically, until we get to hydrides, which are much, much later. So let me give you a couple take-homes that we can talk about in class. Do the Lewis structure for CH3OH. And regarding charge, I have to give you charge. Okay, and actually a better way for me to draw this is CH5O. Right, that's a formula, putting all the hydrogens together. Your job is to start to work on this and be able to draw a Lewis structure. Okay. So I have to give you charge, okay? So that's one we can do. CH5N, that's another one. So take those home and work on those. All right, take home, or we'll work on those in class, okay? Let's do an example. Example with multiple bonds, okay? So we started with some neutral ones. We did one with a negative charge, and then let's do some with multiple bonds. So give you a couple examples. C2H4. What do we want to do? Arrange the atoms. Again, there's certain things that are just sort of intuitive. The carbons have to be bound to each other. Hydrogens can't be, okay? We're going to count up the valence electrons. How many do we have? 1, 2, 3, 4 hydrogens. That's 4, plus 4 from carbon. Twice is 8. Right, that's 12. Okay, you got to get used to these valence numbers. That's why I say memorize the periodic table first and second row. That's all you got to memorize. Okay, and then number them across. So we've got 12, and we need to distribute them. 1, 2, 3, 4. Start with the hydrogens. Knock those out. Carbons. 1, 2, 3, 4. 1, 2, 3, 4. We see a problem, right? If we start forming bonds like we usually do, then we're left over with 2 single electrons kind of floating together. This would be a diradical. A radical is an atom with a single electron, okay, kind of an odd number of electrons. But this is not stable, and we are hinting at how we're going to solve this. We're going to make this into a multiple bond. I'm obviously going to redraw that. It's not a big balloon. So let's redraw this as a double bond. Actually, this is the better angle for alkenes. This is called an alkene. We'll get there. Don't worry about that so much. But the angle here is 120 degrees. Okay, just kind of introduce that. This angle is 120 degrees. That's the best way to represent an alkene, but for Lewis structure purposes for now, that's okay right there. Okay. So that's a double bond, a multiple bond. And then the formal charge is 0 again. Okay, so again, with all this organic, we got to work through this process and understand principles and build up our knowledge. Let's do one more. C2H2. Make sure I have the formula right there. Yep. C2H2. This, again, carbons really have to be bound to each other. We arrange, we count 1, 2, and then we've got 4 from each carbon. That's 10. Let's start arranging electrons. That's 10 electrons. We're going to form some bonds. What are we left over with? This one's a little easier to see with the connect the dots. We've got a triple bond, so we're going to draw it this way. It's called an alkyne with a Y. We'll get to what those are all about. Formal charge is 0, but we can form multiple bonds. Okay, anytime you got extra electrons left over, we form multiple bonds. So I'm going to give you a couple take-homes. HCN and H2CO. Okay, work on those. Maybe we'll do those in class. Okay. So we've talked a lot about formal charge, so let's talk about it. Or we've introduced it, so let's show it. Okay. Formal charge is just that. It's formal. It's a formality. Okay. Think of it as bookkeeping. It's bookkeeping of electrons. We have to keep track of our electrons. That's really important. Okay. A formal charge may or may not be real. The molecule is charged, but there might be a charge on an atom that is formal, in which case there's no electron density there. Okay, we'll kind of point those out as we go, but the point is it's formal. Charge is assigned to individual atoms. This is important. If you draw a charge, individual. If you draw a charge on a whole molecule, it's incorrect. It's formal on an atom. Individual atoms. For our purposes, there's really never going to be more than one on a molecule. Maybe once we'll show something, but that's not what we're doing. Okay, there is one charge on a molecule on a specific atom, and it's always plus or minus 1 if it's not 0. If it's a neutral molecule, formal charge is 0. Okay. Now, with Gen Chem, you saw lots of charged things like 2 plus, 3 plus, 4 plus, and you might have multiple formal charges. For organic purposes, we're really talking about a negative charge or a positive charge, or a neutral 0. Okay, so plus 1, minus 1, or 0. So how do we figure this out? Formal charge, or FC, I'll do in the future, equals number of valence electrons minus number of owned electrons, OE, owned. Okay, so the valence electrons is simply the valence number. Okay, it's the column number, it's the group number. Okay, again, you've got to memorize that. You should know very soon that carbon is 4, nitrogen's 5, oxygen's 6, fluorine's 7. Okay, it should be something that is memorized. So number of owned electrons equals unshared electrons. Unshared are lone pairs. Think about it. If a molecule has a lone pair attached to it, it's not sharing it. Okay, that's one part of the equation. The second one is 1/2 of the shared electrons, i.e. the bonds. Okay, if you think about this, it makes sense. It's the whole point of everything. If a molecule is sharing its electron in a bond, then it only owns that one. Think about sharing something with someone else. If you share a car with someone, then you own that car and you're sharing. It's not their car, okay? If you try to think of another example of something that's not consumed, right? If you share food, it's eaten, okay? But you know, if a kid shares a toy for a period of time, he takes it back when the time is over, right? So, but they can play with that toy together and bond, okay? So you can use that analogy. Play with the toy together and they bond. So they're sharing electrons, these atoms, forming bonds. Half of the bond was the original electron it was sharing, okay? So I can't stress enough, the concepts here are critical to understand, to be able to do the chemistry we want to do later on in the course, okay? So we got unshared electrons, lone pairs, plus half of the shared electrons. Let's do some examples now. Let's calculate. We did this Lewis structure earlier. This is methane. We'll get to names much later. The formal charge is 0. Let's see how we calculate it. So we have this formula. We start with our valence. That's 4 minus the owned electrons. So the first thing you got to do is look at owned electrons. How many does carbon own? In this case, it owns the same number as its valence number. And that is by far the major case. Neutral molecules are the common example, okay? But it owns how many? It doesn't have any lone pairs. So that's a 0. There's no lone pairs on carbon. And it owns 1/2 of the shared. How many is it sharing? 8. There's 8 total electrons around carbon. Hence, it has filled its octet, and it's 1/2 of those, right? It brought 4 in. It shared 4 with the hydrogens, and so it owns those 4. It still owns 4. So it's owned as 4. Therefore, formal charge equals valence electrons. That's its valence number. 4 minus the 4 owned equals 0. Formal charge is often 0. We don't need to write it here, but you can put a 0 there. We don't do that. It's implied. Okay. Again, you should get used to the fact that carbon with 4 bonds to it is neutral. Okay. Carbon with 3 bonds and no extra electrons is going to be plus. Carbon with 3 bonds and a pair of electrons is going to be a negative. Okay. Carbon with 4 bonds is 0. It's neutral. Okay. And you'll learn that for other atoms. Okay. So let's do a couple that are, we'll do 2 more examples, or 3 more. Let's look at our alkene, we call it. Each of these carbons has a formal charge of 0. Why? It has 4 bonds to it. 1, 2, 3, 4 for that carbon. 4 bonds. It's sharing its total shared electrons, again, are 8. It has filled its octet by covalent bonding, but it owns 4. Owns 4. Formal charge, again, is 4 minus 4 is 0. Okay, so formal charge is 0 on both those. Let's look at a carbocation, we call it. Cations are positive. And if that's the molecule right there, we have to assign a charge. So now we have a charge, so let's count it up. The owned electrons are lone pairs. There's none of those. Plus what? 1/2 of the shared. There's 6. Sorry, that's a parentheses. Half of 6. Carbon is sharing 6 electrons. Right? It's trying to fill its octet, but it can't. Half of 6 is 3. Therefore, the formal charge equals 4 minus 3. What is that? It's plus 1, or just a plus. Put a little plus next to carbon. It's called a carbocation. Let's draw a carbanion. Got 2 electrons there. And we got to put a charge there. Owned electrons. Now there's a pair. One pair is 2 plus what? 1/2 of 6. That's 3. 2 plus 3 equals 5. Valence electrons equals 4. So formal charge equals 4 minus 5. Negative. Put a negative next to carbon. Okay. So that's a couple neutral carbons. Cation, anion, carbanion, carbocation previously. So let's do formal charge in other atoms. And actually, I'm going to give these as take home. I want you to work through these. H3O. Again, I'm going to give you a bracketed thing, but you have to put the plus charge on the appropriate atom. And I'll give you a hint, it's not hydrogen. NH4 plus. Again, not hydrogen, so work through that, connect the dots. So now you're doing Lewis structures and you're adding formal charge. So take these home, we can work through them in class. So I'm going to give you an important table that I don't want you to simply memorize, yet I do want you to memorize it, okay? It's hard to explain what I mean by this. I'll talk about this in class. You're not simply memorizing, but memorization should come as a byproduct. And it's okay to commit some things to memory, okay? So I'm going to go ahead and say memorize but understand. How's that? Memorize but understand. Because you want it to be so ingrained that you can move on and do other things. Okay, so I'm going to give you a table here of atom, valence electrons, and then formal charge, and that's going to be +1, 0, or -1. So I'm going to give you the atom: carbon, nitrogen, and oxygen. And I'm going to go ahead and give you X to complete the table here. Just give me a second. We give you X. X equals F, Cl, Br, or I. Okay. So carbon valence number is 4. Again, memorize it. Okay. Lithium, beryllium, boron is 3. Carbon is 4. Nitrogen's 5. Oxygen is 6. X is 7. Fluorine, chlorine, bromine, iodine are all 7. Okay. So what do they look like when they're charged? Carbon looks like this. These are just generic bonds to something. We're not worried about what they're bonded to. You should go through here and put H's on everything. Just practice drawing molecules. Nitrogen 5. Notice there's never 5 bonds to nitrogen. And the reason I say memorize this, at some point it should become second nature. For example, all these should become second nature, that oxygen bound to just one thing with 3 lone pairs has a negative charge. You shouldn't, at a point, you won't have to calculate this anymore, or you shouldn't. And just to add the halogen, let me just put a chlorine there to give you an example. We'll see a couple of these where halogens have 2 bonds. It's not as common. Halogen with 1 bond, call these halogens. So chlorine with 1 bond and 3 lone pairs. Chlorine with 4 lone pairs has a negative charge on it. Chloride. Notice there's never 5 bonds. We call those Texas atoms because everything's bigger in Texas. So a Texas carbon has 5 bonds. It doesn't exist. There's never 5 bonds. You need to memorize that as well. Again, take home, work through all of these, put hydrogens on the bonds, put hydrogens in there, and calculate the formal charge. Convince yourself that it's plus, 0, or negative 1. Okay. All right, that's formal charge. That was Lewis structures and formal charge. So now let's start drawing, and that's why we need to get this down quickly, because we need to start drawing isomers. Okay. 1.4 is isomers. All this means is it's just more Lewis structures. Okay, so it's a different section, but it's more Lewis structures. Different molecule. Isomers, what are they? They're different molecules with same formula. So the ones we've gone over had really one connectivity possible. But we have 2 major types of isomers. Constitutional is what we're talking about right now. And that just means the constitution is different. Different arrangement of atoms. So let's different connectivity. Let's do an example. C2H6O. There are 2 ways that we can connect the atoms. And again, a great way to practice is to go back later. I'm going to do this for you, but to go back later and write down this problem again without looking at the answer. Okay. So how do we do this? We can start to arrange some atoms. I'll do a kind of a really brief Lewis structure. This is one way. Start to connect. Boom. That's called ethanol. Okay. Another way you can start to connect. As you practice these, you'll see there's only so many possibilities. Is this a legitimate structure? Yes, it is. Where are lone pairs? If you go through here and calculate the valence electrons and everything, you should come up with these. This is called an ether. We're going to get into functional groups and different names of things. This is called an alcohol. Ethanol is a type of alcohol. This is called dimethyl ether. We'll get into names later. Okay. All right, so that's a constitutional isomer. And let me give you another one to take home or work in class. C3H8O. So the first step is Lewis structure. You got to draw out the Lewis structure. And there's more than one. There's actually three. So I'm going to give you that hint. There's three legitimate ways to connect the atoms. Okay. You actually get two OHs, and you'll get one that's another ether. Okay. So do that one. Take it home. And the second one, the second type, we're not going to talk about this yet, are stereoisomers. So there's two types of isomers: constitutional isomers and stereoisomers. We'll talk about that in chapter 4. All right, so that's a brief intro to isomers. 1.5 is just exceptions to this octet rule. It's not really a rule, okay? It's a rule for the second period. It's a rule for the second row, but it's just what we call the octet rule. The first exception is not really an exception because it's in the first row, so that's not the octet rule. It's the dual rule or something. You can only hold 2 electrons, okay? But second row elements, such as beryllium, because beryllium's valence number is 2, it can only form 2 bonds, at least with the electrons that it has available. Okay, so BeH2, for example, simply can only has 4 valence electrons available to bond. 2 from the hydrogen, 2 from the beryllium. Okay, we'll talk about some things about this later. Okay, another example is BH3. Same principle. Boron's valence number is 3. It only brings 3 electrons to the table to bond with. Hydrogen brings 3, so neutral boron can only have 3 bonds. Okay, there's only 6 valence electrons to bond with. Again, all of these examples, you need to go through them and work through the Lewis structure and understand. So that's a couple exceptions of not enough, and other exceptions of too many quotes. And all this is now we're just going to glimpse at the third row or the third period. We're going to look at sulfur and phosphorus. This is not that big a deal. We're going to see some reagents later, but this one is called DMSO, and it is, let's draw this out. It has sulfur in it. And there's a couple ways we can draw this. This is really just an intro. I just want to introduce this. If you were to draw DMSO, you'd come up with something like this. There's something called a resonance form that we'll talk about later, but this has, so it's too many electrons. If we counted up sulfur, we'd come up with 10 electrons around sulfur. Well, the argument is that sulfur has d orbitals and can hold more electrons, okay? That's a bit of probably a misnomer. There's another thing we can draw here, but I just want to draw your attention to sulfur and phosphorus are going to have, look like they have 10 electrons, okay? So let's draw sulfuric acid. Put all the electrons in here. You've heard of sulfuric acid. There is a reason I'm angling these bonds. I'll get to that later. It's a habit because it's the right way to draw it. But if you put all these electrons in here and you counted them up, you'd actually count 12 electrons to sulfur this way. It's called sulfuric acid. Let's look at a phosphorus example. Phosphoric acid looks like this. Probably heard of phosphoric acid. It's in the soda that you often drink, which isn't good for you, but that's all right. Put in some electrons here. All the oxygens have pairs of electrons, and you would say there's 10 electrons around phosphorus. 2, 4, 6, 8, 10, okay? So just an introduction. D orbitals are kind of the common explanation. It's really more complicated than that, but that's okay. So that concludes this lecture. We'll stop here. We'll pick up with resonance on the next lecture.